Now we move to C4. Projectile motion. And this is the classic problem where something takes off from the ground, like you're kicking an American football, say, in the US football, and then it goes up like this and comes down. So here there's some initial velocity at some initial angle. Some books will put a little sub-zero for the initial angle, but I'm not, because I'm going to just have the one angle in the problem that we're going to set up. We're not going to be analyzing angles as we go. This is called the range. And here you have X and you have Y motion. You have a two-dimensional problem. So what we do is we're going to use our basic kinematic formulas. And for the X initial velocity, you could do it like that, X sub naught T plus at 1/2 A sub X T squared. And then for the Y, you would have a Y naught plus some initial velocity in the Y direction plus 1/2 acceleration in the Y direction. All right, now things are going to simplify because we're going to pick the origin here where it starts to be 0. So that means these are gone. This is going to be V naught cosine of the angle to get you the velocity component. So you have a velocity like this. You can think of it as having two components that, see, if I draw this vector like that, let me try a different color here, see what happens. So we can think of this vector as having two vectors, where there's one here in the X direction and one going up. So this would be, if we now label this V naught, and this the angle theta, this is V naught cosine of theta, and this is V naught sine of theta. So that's what we're going to be doing for the two velocities. And then there's no acceleration in the X direction. We do a problem with no air resistance. And if there's no air resistance, then this AX is 0. And then here, the AY is simply minus G due to the gravity. Since the Y, is positive going up, then I need to have the negative sign. Remember, G, it's by itself is always positive, and that's our convention. So these equations simplify. You get V naught times the cosine of theta times T, and then we get Y is equal to V naught sine of theta times T minus 1/2 G T squared. And these are the equations. Now what we would like to do is find Y as a function of X, like in math class, where you have your X and your Y. So if we want to do that, we want to get rid of the T. So we use this equation to get T is X over V naught cosine of theta, and we stick that in here, and we stick that in there. So that gives V naught sine of theta. We put this in, so we're going to have here X over V naught cosine of theta, and then a minus sign, 1/2 G, and we're going to stick it in for the time. And now let's work it out. Well, this first one kind of simplifies because this V cancels and you just have the tangent. So this is the tangent of theta times x, we could do that and make it clear, minus, and here you would have in the, say, numerator a g times x squared. Then down here would be a 2, the v naught is squared, and the cosine is squared. So like that's it. This is it. That's the equation. Now, does it make sense? Remember, we always like to stop and pause and see if answers are reasonable. Well, this is an upside down parabola because of the minus x squared. Look, upside down parabola. And this linear term in x means that the parabola is like shifted. So we have a shifted parabola. Makes sense. Now, the range is very, very important. So we're going to analyze the range. And to do the range, notice that the y is 0. So when I first started teaching this course, I remember many, many years ago, I set y equal to 0, and the student says, wait a minute, or something. She said it's easier to set the y equal to 0 with the time and solve for the time, and then put the time into the x. And sure enough, she was right. So I'm gonna do that. It's a little bit easier to work with this equation. It looks friendlier than this one down here. So we're going to set the y equal to 0 up in this equation. So we're going to use then the y equation with the time. So we have the sine of theta like this, and we could group that times t minus 1/2 gt squared equals 0. So we're going to find the time it takes. Well, actually, we're going to find 2 times. We're going to find the time when the y is 0. So the y is going to be 0 2 times. It's going to be here at t equal to 0, and also at t equal to time of flight, which if you want, you could use like some capital T. So here, what we do is we factor out, we don't divide by t. Never divide by, when you're doing a solution, you'll lose a solution. So what we do is we factor like this, minus 1/2 gt. We pull the t out, we factor. So now we can see that to get 0, we have 2 ways of getting 0. We could have one way where t is equal to 0, and that's at the beginning of the trip, up here. And we could have the case where this is 0, v naught sine of theta is 1/2 gt. So t is 2 v naught sine of theta over g. And that's going to give us the time of travel of the trajectory. So now what we're going to do is take this time and plug it in to the x equation. So remember, x is v naught cosine of theta t, a very, very simple equation. So we're going to want to put this t in there. So when we do that, we get the range. So we'll call this now the range. When we put in the t that corresponds for the entire trip, you get the range. So this is v naught v naught cosine of theta. All right, that's what this is. And the time is then this one. It's a little bit tricky how it's crossing around here. 2 v naught sine of theta over g. So that would give me here, that's going to give me v naught squared over g times 2 cosine theta sine theta. And I pulled the 2 over because, see, this is a trig identity that's equal to that trig identity, that's sine of 2 theta. So that makes the R equation very, very nice. V naught squared over g times sine of 2 theta. And if you want to put a little sub-zero there, you can, to emphasize that that is the initial angle. I'm going to leave it the way it is there. Notice that to get the maximum range, you want this to be maxed out, and the sine is maxed out to 1, and that's going to happen when you have 90 degrees for the 2 theta, which means theta being 45 degrees will get you your maximum distance. If the angle, for example, is like straight up, you're not going to go anywhere. So this is showing you that you get the maximum distance. Like if you were kicking, say, a US football, if you kick it at 45, you get the max. Now you got to be careful when you do the real world problems, because in baseball and football, you got air resistance, and that, and you got the human body, what's the way to kick or the way to hit the ball with the bat. So you find that here there's some going to be deviations from the ideal physics. But anyway, ideal physics says 45 degrees gets you your maximum range. Okay, what we would like to do next is the maximum height. The maximum height's a nice thing to look at also. That would be, see here, that's going to happen in the middle. That's going to happen in the middle. So the halftime is going to be 1/2 of the time of the trip, which we solved, we have down here. So we will copy this again, which we already found to be 2v0 sine theta over g. So the half time is that. Very, very nice formula. And I'm going to include the 1/2 subscript there to remind me. So the y max is going to occur. Now here's the y equation, v0 sine of theta times t 1/2 mark minus 1/2 g t at the 1/2 mark squared. So we're going to put this in for the t in these both places. So the max is going to be v0 sine of theta, and this is going to be v0 sine theta, hey, how about that, over g, minus 1/2 g, and we're going to square this thing, v0 sine theta over g squared. Now this is interesting because this first term is v0 squared over g times sine squared theta. But the second one, when you square the g in the denominator, you'll have a g down there, you'll have your v0 squared, you'll have your 1/2 here, you'll have your v0 squared over g. You get the same kind of a term, just with the 1/2 in front. So 1 minus 1/2 is going to be 1/2. So this is the formula for the y max. That's a cool formula there. I'm going to write that one as v0 squared sine squared theta over 2g. I think that looks cool. All right. Now what I would like to do is another way of doing this, and to check on reflection, it's good to check things. I would like to find the maximum by taking the derivative. In other words, this y is going to be a maximum here. I'm going to take the derivative, set equal to 0, because when you do that, when you have a function and you set equal to 0, you get either a maximum, because that's the slope, derivative is the slope, or you get a minimum. So here I'm going to take y, which is v0 sine of theta times t minus 1/2 gt squared. I'm going to find this time another way. rather than doing the 1/2 thing to just check. So this is going to be a check on my time. So if I take the dy dt, the derivative here would be, some constant times t. The derivative is then, you just pull that constant off. And then here, when you have t squared, the derivative is you pull the 2 down, 2t, and then for the exponent, it's 2 minus 1. So that's what it is. And that's going to be equal to 0. So that means v naught sine of theta minus gt is 0, and that means t is v naught sine of theta over g, and here, that's the halftime. So it's kind of neat to do it both ways, and also reviews calculus, differential calculus. Now notice another cool thing is if you take the second derivative, so here is the first derivative, there's this part in, here's the first derivative here. The second derivative is simply minus g, and that's less than 0, and the rule is if the second derivative is less than 0, you don't hold water, you got something like this, you have a maximum. If the second derivative is positive, then you hold water, you have a minimum. So that's a cool trick. So here the second derivative is negative. Notice that the second derivative of y with respect to x is also negative because, see, this starts out with the greatest slope, steepness, and then it gets less and less, and here you have 0, and then here you have negative slope. So at all points, the second derivative, which gives you the change of the slope, is negative. So that's a nice little review of calculus. Differential calculus. We didn't really need it. We did everything without calculus, but it's kind of cool to review some calculus.